All right, hello everyone. So my name is Ben Letson, and today I'll be giving an update for the team at the University of Florida on the long-term reliability testing of the UV LEDs for the LISA charge management device. So I'm going to share my slides, and then I'll disappear for a little bit. So a very quick background of what we're doing at the University of Florida. So as part of NASA's technology contribution to LISA, we will be developing the LISA charge management device. So the CMD is tasked with delivering UV light to the GRS to discharge the test mass. And so the LISA CMD will be heavily based on the design of the LISA Pathfinder CMD with one key difference. So the LISA CMD will use state-of-the-art UV LEDs as the UV light source rather than the mercury vapor lamps that were used on LISA Pathfinder. And so while these LEDs do give us a good number of advantages over the mercury lamps, they are a relatively new technology, and so they only have a small flight heritage where a few devices were used in low Earth orbit for about 1 month. So these devices do still need to be space qualified for use for LISA. And so part of the tasking we've been doing at UF is the performance testing of these devices, which is complete, and we have one publication that's under review right now, where we'll be publishing some of those results, so keep an eye out for that. But a second effort with the space qualification of these devices is the lifetime testing of these devices, and where we're aiming to show that these LEDs will be able to survive the nominal 4-year science mission for LISA, and they'll be able to support any of the 6 discharge modes that we're required to support. So while these LEDs, one of the big advantages of these LEDs is that we're able to pulse them in sync with the 100 kilohertz injection signal inside of the GRS, which allows us to use some more robust modes of test mass discharge. And so these modes can be broken down into 2 different types. I have all 6 listed here in this table in the bottom right. So these discharge modes can either be categorized as intermittent discharge modes, where the LED is, or where the charge of the test mass is allowed to accumulate over a period of maybe 2 weeks, and then in a span of 10 minutes, the LED is turned on and brings the charge of the test mass from some upper limit to some lower limit, and then the charge management device is turned off and the charge of the test mass is allowed to accumulate. And so in these modes, the LED has a very small amount of fractional on time over the course of the LISA mission. However, the second type of discharge mode, and the ones that are deemed the highest risk, are these continuous discharge modes, where the LEDs are on at a very low power to offset the environmental charging rate. However, these are deemed highest risk because they do require the LEDs to be on for the majority, or for the entire LISA mission. And so at the University of Florida, we performed 2 different lifetime tests looking at all 6 of these discharge modes, and I'll cover the results of these tests now. So the first lifetime test we did, the key result of this test was the investigation of the intermittent discharge cases, where we tested LEDs at 4 different temperatures between 20 degrees and 80 degrees C. And these devices were stressed at constant driving settings while the relative power output was monitored. And so one of the biggest takeaways from this test was that the temperature of the LED is one of the biggest drivers of the rate of degradation of these devices. But if we only consider realistic spacecraft temperatures from LISA, so for this test, our devices that were at 20 and 40 degrees C, the intermittent discharge cases are no issue. So for a worst case intermittent discharge, this would require the LEDs to be on for about 600 seconds once every 3.5 days. And so over the course of the 12.5-year LISA mission, this only equates to about 9 total days of on time. And so if you look at the plots in the bottom left and top right for the DC and pulsed intermittent modes, after 9 days of on time, the LEDs in these modes have lost no more than about 30% of their initial output power. And then over the 191 days of testing, we saw no failures in these devices. And so that equates to over 15 LISA lifetimes and gives us a good confidence in the viability of these intermittent discharge modes. And so we have a second lifetime test that's in progress right now at the University of Florida. And so this test is designed a little bit differently. First of all, we're specifically looking at the continuous discharge cases. We're testing 96 LEDs in the 2 different continuous discharge modes. And so this test is designed to change, to constantly update the driving parameters of the LEDs to maintain a constant output power as the LEDs degrade. And so for the first case, we can look at these LEDs in what we call the quasi-DC case, which is a 1 Hertz pulse width modulation. These quasi-DC devices are being driven to maintain 1 nanowatt of output power. And so this leads to initial driving settings of 20 milliamps of drive current and a 0.1% quasi-DC duty cycle, or 1 second duty cycle. And so something to note here about these plots in the bottom. So since the driving parameters are being changed to maintain a constant output power, the lifetime results are showing a change in what we call the integrated current, which is effectively the 1 second average current given to these devices to maintain this initial output power. And so for the over the first 600 days of testing, so far the devices at 20 degrees C, most of these are requiring 10% more integrated current than at the start of the test or less. And then in the 40 degree case, at the hotter case, the majority of these devices are requiring between 5 and 30% more integrated current, whereas we have a handful of devices that are requiring maybe up to 70% more power than at the start of the test. And in the second case continuous discharge mode, we have LEDs being driven in a pulsed mode. So these LEDs are being driven to maintain 4 nanowatts of output power, and this means that these devices at the start of the test were being driven at 20 milliamps, 2,000 pulses per second out of a possible 100,000. And so for both the cases at 20 and 40 degrees, we have most of these devices are requiring 10% more integrated current or less. There's a few outliers in these cases, but the vast majority of these 48 devices are still very close to their initial output power. And so because these LEDs so far are performing much better than what we initially expected, it's interesting to project this current performance out over the course of over an extended period of time. So the initial plan was to show that we have a high confidence that a single LED will last for 2 years, which is why this current test is going to run for 2 years at least. And then we could show through system redundancy that we have a really high confidence that the charge management device will be able to perform continuous discharge for the 4-year science mission with 2x redundancy. However, because we are seeing much better performance, in order to get an idea of what this current performance will look like over an 8-year or an extended period of time, in this case 8 years, we ran a Monte Carlo simulation of the lifetime projections. So we could say that in a worst case scenario, the integrated current will grow exponentially due to a sort of positive feedback loop where as the LEDs lose power, they're given a higher driving stress to maintain the constant output power. And then this in turn causes faster degradation of these devices. And so to account for this, we fit an exponential model to each of the cases or each of the devices from all 4 cases. And then using the sample statistics of the exponential fit, we generated 10,000 simulated devices for each of these driving cases and projected these the lifetime or the integrated current growth out over 8 years to get an idea of the integrated current distribution at the end of 8 years. And so this table in the top right shows the 99th percentile relative integrated current after 8 years. And so maybe the most concerning number in this table would be the quasi-DC 40-degree case. The Monte Carlo projections are showing that after 8 years, the 99 99% of these devices will be using 39 times more integrated current at the start of the test or less. And so while this number does look high, especially compared to the other 3 cases, it is worth noting that because the initial output power was so low for these devices, this only equates to a 4% duty cycle of the quasi-DC or in the quasi-DC mode to maintain this constant output power. And so because we can go up to a total of 100% duty cycle, there's still plenty of headroom to account for further losses in power. And so we have several more papers on the way showing how we can improve on these lifetime projections through some simple screening methods through our initial device characterization tests and improve these Monte Carlo results even further. And so the last thing I'll talk about in terms of LED reliability is some of the recent radiation testing results that we've done on these LEDs. So back in May of 2022, several of us from the University of Florida took 8 LEDs and 9 silicon carbide UV photodiodes out to a radiation testing facility at UC Davis, where we performed radiation testing on these devices and ended up exposing them to all the way up to 1,000 kilorads of radiation, which is 10 times more than the expected LISA exposure. And so as expected, both of these devices are extremely radiation tolerant. So these UV LEDs at nominal operating currents, so in this case 20 milliamps, the output power was unchanged by within 1% of the initial output power of these devices for all LEDs. And then the photodiodes with the largest sensitive area, or all the photodiodes experience a gradual decline in the UV sensitivity over the course of the test. And then in this plot, we're showing the devices with the largest sensitive area, where these decreased by maybe up to 20% after the 1 megarad exposure. All right, so that's all I have, everyone. Thank you so much for listening. And if you have any questions, you can leave a comment on the video and I'll try to get back to you, or you can send me an email here. But again, thank you for listening and have a great day.